In this video, we'll take a look at interpreting spectroscopy. So mostly I'm going to focus on infrared spectroscopy, proton NMR, and C-13 NMR. Now, this is going to be the first video in a series of videos in which I'm interpreting these spectroscopy questions, and I intend for each video to have about 5 questions that we will solve under different functional groups and different categories like that. So with that, we'll get right into it. So these questions are all going to be a series of all the spectroscopy data that you could get for a particular compound. So there's a lot of things that you could look at initially. You're going to have a infrared spectroscopy and a mass spec and UV spectrum if that's relevant to the compound, which will depend on if there's any pi bonds or triple bonds, which are also pi bonds, but 2 pi bonds in the triple bond character. So with that, let's jump right into it. And the first thing that you should look at is the mass spec, which tells you the molecular formula, right? Which is, in this case, it's C4H8O. Okay, so then the next thing you should determine is the degrees of unsaturation, DOU. And this is the number of rings or double bonds that are present in the molecule. And to determine this, it's first the 1/2 of the number of hydrogens that would be present if this was saturated, minus the number of hydrogens that are actually there, and then minus any halogens, which I'll indicate as X, and then plus any nitrogens if you have them. So here, what I mean by H saturation, this is 2 times the number of carbons plus 2. That is always the formula for a fully saturated hydrocarbon. So here, in this case, our DOU is then going to be 1/2. H saturation is 2 times 4, which is 8, plus 2 is 10. So H sat is 10, minus how many there are actually present. There's 8, and then there's no halogens. It's simply just an oxygen, and there's no nitrogen. So we don't have to add anything else. Oxygen is not included in either of those. So then this is then 10 minus 8 is 2, divided by 2 is 1. So there's 1 degree of unsaturation. So again, this means that there's 1 ring or 1 double bond, pi bond here. Now, a question that I should answer now, which isn't relevant to this problem, but if you had a triple bond, that would have at least a degree of unsaturation of 2 for each of the pi bonds in the triple bond, okay? So then next thing to look at is the IR. There's really no rhyme or reason to how you proceed, but it's best to start with the degree of unsaturation to limit how many options you're going to have. So the next thing I like to look at is the infrared spectroscopy, and what we see is a significant peak at 1718, which corresponds to a carbonyl, which is C double bond O. So then, using the information that we have from the degree of unsaturation and the IR, we know that the only degree of unsaturation is in this carbon-oxygen double bond. And then we see some other stuff throughout the fingerprint region. This is probably a carbon-oxygen single bond, which is a part of the double bond here. Remember that there is a carbon-oxygen pi bond and a carbon-oxygen sigma bond in that double bond. And then these are all going to be carbon hydrogens, sp3, because they are around 3,000. They're not above 3,000. And remember, sp3 just means that they're all sigma bonds. There's no alkene or alkyne nature of it in this molecule. So, and then I'm not going to interpret the mass spec because we can take a look at this, but it's not necessary to solve most spectroscopy problems. If you're given the proton NMR and the carbon NMR, those 2 things give you enough information to solve the problem without the mass spec. But you could be asked about a problem where you have to interpret it based solely on the mass spec. So anyway, let's get into the proton NMR and the carbon NMR. So here is the carbon NMR first. And what we see at the top is the proton coupled, this top line here versus the decoupled. So this tells you how many adjacent hydrogens are bound directly to that carbon. So in this case, we see here's our signal in the first one, this first signal here, which has 3 peaks, or 4 peaks rather. So that means n plus 1 is 4. So the total number of hydrogens bound to that carbon is 3. So this is a CH3 because we see a quartet. Simply because we see 4 peaks, we know that that is a quartet. Same with this next one. And then this is a CH2 because it's a triplet. This one's a little bit more confusing because what you see is a quartet that's almost overlapping with a triplet, but there is enough separation there to resolve those. So this is a CH3, CH3, CH2, and then this is not split at all. So that is just your carbonyl, and it's also very, very high, so that is likely to be a carbonyl. Now, secondly, when you have a quaternary carbon above 200, that is very indicative of a ketone in terms of above 200 chemical shift for a C-13 NMR. So this is probably going to be a ketone based on that signal there. And then this would make sense, the CH2, since it's split downfield, that it would be adjacent to the carbonyl. And then this CH3 must be adjacent to the carbonyl as well, since it's very far downfield. And then this molecule must be, this CH3 must be bound over here. So this is likely our structure. We'll corroborate this with the proton NMR next. That is much more compelling evidence. But this makes sense here because we see our ketone, we see our CH3 that is shifted downfield, that is this one. We see our CH2 that is also shifted downfield, that is this one. You may wonder why the CH2 is more deshielded than the CH3, and it's due to the presence of the adjacent methyl group as well. All of these features of chemical shift is additive. So the idea that we have a CH2, CH3 next to a carbonyl is why it's shifting even further, is because it's being shifted by the carbonyl and the CH3 group. And then lastly, we see the CH3 that isn't shifted significantly because it's only bound to another CH2 group. Okay, so that's the C-13 NMR. Now let's move to the proton NMR. So here we aren't given how many hydrogens are representative of each peak. We're only given the integration as these vertical lines. So you may be asked to do this on an exam, so I'll do it once per video in these series to show you how you interpret this. And what I mean by that is how to determine the number of protons that are there. So what you got to do is get a ruler out. So your professor may require that you need a ruler for exams. And you're measuring this line here, not the line that's showing the splitting, but the line in between these two, right? So you're measuring this distance here that I'm indicating in blue to make it more clear. Same thing here. This is what we're measuring when we talk about integration. And then here as well. Then I like to measure this in centimeters because it's a lot easier than working with inches since these are small sizes. So here, you don't have to be perfect on these measurements, but that looks about 1 centimeter to me from the bottom of that line to the top of that line. So we will call this peak is 1 centimeter in integration, the area under that curve, under those peaks. This one also appears to be 1. Again, maybe slightly higher, but you don't need to be perfect in these measurements. It's just to give you the ratios. And then lastly, this one is maybe 0.6, 0.7, call it 0.7. Okay, again, you don't need to be perfect here to measure these. So now you have to add all these up in terms of the total measurement, the total distance that we see there. So what that is here is 2.7 centimeters, and this is representative of all the hydrogens. So we have to go back to our formula, it's H8. So 2.7 centimeters is 8 protons, 8 hydrogens. So then one hydrogen is simply 2.7 divided by 8. So I'll grab my calculator here, 2.7 divided by 8 is 0.34, rounding up there. So that what this means is 0.34 centimeters is 1 hydrogen. So then a peak that is 1 centimeter, if you multiply this by 3, it's going to be slightly over 1. And again, it doesn't need to be critical here. Like it doesn't need to be exact. So this is 3 hydrogens. This one is 3 hydrogens. And this last one is 2 hydrogens, the 0.7. And if that didn't make sense here, I'll do it slightly more deliberately. So if you look at this 1 centimeter peak, so that's our 1 that we include there, and we divide this by the number of the distance per hydrogen, and that will give us the number of hydrogens that are there. So that is what we get here, and that's 2.95. You can't have a fraction of a hydrogen, so we round that up to 3. That gives you the same exact value for this next peak, and then again you do it for this last one, which is 0.7 is the total peak divided by 0.34. That is slightly over 2. Again, that is, you round to the nearest whole number, which is 2 in this case. So then we have a peak of 3, 3, and 2. 3 plus 3 plus 2 is 8, which is consistent with our molecular formula, so this makes sense. So now we need to determine if our proposed structure is consistent here. So in this peak, we see a 3 hydrogen triplet. It might be a little bit hard to see because of my blue line that I have here now, but this is a 3 hydrogen triplet. So what that means is that this peak here, let's call this A and B and C. So our A peak is a CH3 that is bound to a neighbor that has 2 hydrogens there. Since it is split into a triplet, it must have 2 hydrogens splitting it, and then n plus 1 gives us the triplet there. So then if in this moiety, this CH2 then would be a 2 hydrogen signal that is split by 3. So it would be a 2 hydrogen quartet. Let's look at our NMR, and do we see that? We do see that around 2.5. There's a quartet here that I've labeled C, so that's this those hydrogens there at that carbon. That's a quartet. There's 4 signals there, 4 peaks. And then lastly, there's around 2, there is a 3 hydrogen singlet, so that has no neighbors. So that must be bound to our carbonyl, because if it was bound here at the C carbon, it was bound to the C carbon, then it would have a splitting there. It would be a triplet as well. So this is also consistent with the chemical shift that we see, which is about 2. A methyl group bound to a carbonyl is between 2 and 2.5, so that makes sense. And again, we see that this CH2 group is also shifted downfield slightly. And again, these are all additive, so this makes perfect sense that our structure would be like this, where we combine these 2 fragments together to get that. And now here, this is the B signal here, those hydrogens. So now I will redraw this once more in a different color and in a skeletal format here to show how you should include all this information on an exam to give you the maximum points. So for C-13 NMR, you should say that, label these somehow. I say A, B, A to D. So A is the 3 CH3 group that's bound to the carbonyl. So that is here, because we see it shifted to around 35, close-ish to 40. So that's consistent there. And then our CH2 group that's bound to the carbonyl, that is C here. And then D is the least shielded, or the most shielded, the least deshielded signal there at the lowest number. And then our ketone is last, which is B here. Okay, that labels all of the signals. And then again, you do the same thing for this last one. So here, for the proton NMR, I should say, so A here is the singlet. And then you don't see any signal for the quaternary carbon here, since this is proton NMR. B is then the CH2, that's a quartet. and then C is the CH3 that's a triplet. Okay, so hopefully that makes sense. So now I just illustrate the difference here between like interpreting the structure and then finally submitting your answer. So you should do this on like scratch paper or something, and then on your final exam include just what I've labeled in red, and that will give you the most points for the proton NMR and carbon NMR. If you had to look at the IR to get points there, again, the only key feature here to recognize is the carbonyl. Everything else is not informative to tell you the type of structure that you have. And again, the mass spec, you can get some information from it, but the proton NMR and carbon NMR by far are more compelling in structure determination. So unless it's strictly specified in the question, you don't even need to indicate anything regarding the mass spec, simply just getting the molecular formula from the mass spec and then determining the degrees of unsaturation. All right, here we have another question. So again, this is just determine the structure based on all the spectral data. So the first thing that I always suggest you start with is the degree of unsaturation from the molecular formula, which we have C3H6O2. All right, so our degree of unsaturation is 1/2 minus, or 1/2 the number of hydrogens if it's saturated, which is 2 times 3 is 6, plus 2 is 8. That is H saturation. And then we subtract the H that is actually there, which is 6, and then minus halogens plus nitrogens. There aren't any here, so this is just 8 minus 6 is 2, divided by 2 is 1. So there's one ring or one pi bond. Okay, now if we look at our IR next, we see a signal at 1715. That is indicative of a carbonyl. So this is likely our degree of unsaturation. We also see a very broad signal between 3500 all the way to 2500. So this is likely an OH. And when it's this broad, it is likely part of a carboxylic acid. But let's say you didn't remember that, but you can just call that an OH and you can still get the structure. So anyway, that is what you would include there. And then we can move to the C-13 NMR. So here, this is our depth spectrum instead of the proton coupled and decoupled that we saw in the previous example. And the depth spectrum is more informative because it tells you the type of hydrogens. I mean, so does the proton coupled, but it's a little bit more clear since it tells you that signals down are CH2, ones up can be CH or CH3, instead of interpreting the splitting pattern, which in some examples can be ambiguous. It wasn't in the last one, but if you had signals overlapping, it can make it more difficult for interpretation. But with all that, what I'm saying here is this is a CH2, unambiguously a CH2. This has to be either a CH or a CH3, and we don't know which one at this point. The proton NMR will help elucidate that. And then the depth spectrum doesn't show the quaternary carbons, so that's why in the proton decoupled, we see the quaternary carbon here at around 1700 or so. So this is likely not a ketone because we see the carbonyl, the quaternary carbon, isn't at above 200, which was like the example in the previous question. So all of that is all we can get at this point from the C-13 NMR. So then we have to move to our proton NMR. And what we see here, first of all, is that we have a exchangeable proton. So we know that that is of an OH. And before I continue, I did the exact same analysis that we did in the previous questions, where I measured the distance of the of these lines here between the integration values that we see here to determine the number of hydrogens. And I just am telling you what they are to save some time, but you follow the exact same process that we did in the previous question. So anyway, with that then coming back to what this is telling us, since this is exchangeable, that tells us that it's an OH or an NH. It's just it's a hydrogen bound to an oxygen or nitrogen or a sulfur or something like that. But based on what we see in our chemical formula, we only have oxygens. So this must be bound to a oxygen to be exchangeable, this OH. And again, we see it so high, that's likely of a carboxylic acid, but that's not necessarily factual, since these can vary. The chemical shifts of these exchangeable protons can vary a lot. So we're not even going to say that, but we know that it's just an OH. That's what we have for definitive information. So let's move to the other signals. We have a 3-hydrogen triplet. Again, this might be hard to see because of the lines kind of get in the way, but it's a 3-hydrogen triplet, which means that it is a CH3 bound to a CH2. Because the 3 hydrogens, that is the signal that we're seeing, is the 3 hydrogens here at A. And then A is being split into a triplet, which means it must have 2 neighbors, which is like what we see here in this ethyl pattern. So then if you look at B, B is a 2-hydrogen signal that must be split into a quartet, excuse me. It's split by 3 hydrogens, so that means it has to show as a quartet. And that is in fact the case here. We see that with B. So A is then this methyl group bound to the CH2. So collectively we see an ethyl group. And that's it. We don't see anything else. But we know that there's one more carbon and there's 2 oxygens. So the only way to put this together to retain an ethyl group is if the remaining carbon, I should say, is part of a carboxylic acid. So here this shows the OH, the exchangeable OH, the carbonyl, which we saw in our C-13 NMR, and then we see the ethyl pattern that we see in the proton NMR. So this is the only way to put all this information together such that it's still consistent with what we see in all forms of all the spectral data. So, and then again, let's put this all together to show how you would put this on an exam, again, to get maximum points. You show here your carboxylic acid, which looks like that, and then your ethyl group there. So now let's call this A, the carbonyl, carboxylic carbonyl. B here is this CH2 group that again is more downfield because it's adjacent to the carbonyl. And then C is our ethyl group, or the CH3. So again, from the depth spectrum, this is still makes sense because it could be a CH or a CH3. And CH3 is one of those options, and that's what we're suggesting that it is. So that's corroborated with what we see there. Okay, and then lastly, you should show the same thing for the proton NMR. So this one is A, the methyl group, and here is B. So again, A and B. And then lastly, don't forget this, as I was about to, the exchangeable proton is C here on the OH. That is this signal there. And by the way, I should have mentioned this in the first question, but TMS is tetramethylsilane, which is the solvent for most of these typical NMR experiments. That is completely unrelated to the actual interpretation of the structure. These type of signals are going to be present in all of the molecule, in all of these spectral data, because again, you have to actually dissolve your compound in a solvent for it to undergo these types of NMR stuff, because most of the time your organic material is going to be a solid, and the solid state NMR is possible, but again, that can get more complicated. So anyway, that's the point of this TMS. And then again, the solvent here is not specified in the case of C-13 NMR, but again, it's just a solvent peak. It's not relevant to the interpretation of the structure. All right, here we have another question. So again, you should always start with the degree of unsaturation, in my opinion. So the molecular formula is C4H8O2. So our degree of unsaturation then is 1/2 the number of hydrogens that are saturated. So that would be 2 times 4 is 8, plus 2 is 10, minus how many protons there actually are, which is 8. And then again, there's no halogens or nitrogens, so that's it. So 10 minus 8 is 2, divided by 2 is 1. So there's one ring or one double bond. And here, again, we see a 1700 signal. That's probably a carbonyl. When you see these broad signals here, this is indicative of a CO. carbon oxygen around 1200, 1250, and this is likely a part of an ester. But again, let's say you didn't remember that, so you could interpret that it's an ester from other information, other spectral information. And then the IR spectrum at 2984, these are just carbon hydrogens that are sp3. So nothing out of the ordinary there. No real information is gained from that. And then again, I'm going to ignore the UV spectrum, but there's some information that you can get from that. But again, if you have a really good understanding of C-13 and proton NMR, you can determine the structure without those aids. They will just corroborate what you find. So let's see what we have with the depth spectrum. So this looks like a CH2 because it's down. These can either be CHs or CH3s, either one of them. And they're in different chemical environments because their chemical shift is different. And then again, this is our carbonyl or C-double-bond-O, and this is in the region that an ester could appear at 170 or so. It's just definitely not a ketone because it's not above 200, so we know that much at least. And we know it can't be an amide, right, because there's no nitrogens in our molecular formula, stuff like that. So this is all we can get really from the carbon NMR without just making a guess. So then we need to move to the proton NMR to get further information. So again, like I did before in the previous question, I'm just providing the number of hydrogens that are at each signal without actually doing the measuring to determine how many there are. So with that, let's look at this signal here. So at around 1.2, I'd say, this 3 hydrogen signal is split into a triplet. So again, this is indicative of a ethyl group, an ethyl pattern, assuming that you see a CH2 that is split into a quartet, which is exactly what we see here. So this is A, where this CH3, the 3 hydrogen signal, is split into a triplet because it has this neighbor B that has 2 hydrogens. And this 2 hydrogen neighbor is split into a quartet, which is, again, it's consistent here with an ethyl pattern, like I'm explaining here, right? So the only thing that's unique about B compared to the other questions that we've seen is B is split very high. So what that means is B is probably not bound to a carbonyl. Because if it was bound to a carbonyl, like we saw in a previous question, it would be, 2.5 to 2.7, something like that. It's not going to be all the way up to 4. So that means that this needs to be bound to something that's more electron withdrawing than the ketone, or not the ketone, the carbonyl rather. And the only thing that we could have here is an oxygen, right? That's the only other option that we have that would be more electron withdrawing here. And it's worth noting that this is electron withdrawing, but that's a very different nature than when you're talking about electron withdrawing and electron donating in terms of aromaticity and aromatic substitution reactions. So I just want to mention that. But in terms of this case, all we're really talking about is electronegativity, and these oxygens are going to de-shield the carbon, the hydrogens bearing these on that carbon, much more so than like a carbonyl would. Right, so here, this then explains why B would be at around 4, is if it's bound directly to the oxygen. And then the only other signal that's left is this 3 hydrogen singlet that's around 2, and this is indicative of a methyl bound to a carbonyl. That's why it's a singlet, because there's no neighbor that has a hydrogen. So that makes perfect sense. And then you have to retain the ethoxy group, the oxygen with an ethyl group. So the only way to do that is to connect the oxygen here to the carbonyl. So that gives us our structure like this, right? So A is here, B is here, C is here. Okay. And then same type of information you should provide for the carbon C-13 NMR. So this is A, which would appear about here. Again, A. So we have two. Here, let me label all these first. So we have two CH3 groups, A and D. A is going to be more deshielded than D simply because A is bound to the carbonyl, whereas D is bound to just a CH2. So that's why I get this distinction. And then C here is a CH2 that's bound to the oxygen, which is going to be much more deshielded than either A or D. And then lastly, you have the carbonyl, which in this indication is B. And that would give you maximum points for this type of question. All right, here we have another question. So again, you should always start with the degree of unsaturation from the molecular formula. So we have C4H8O2. This is exactly the same formula that we saw in the previous question. So our degree of unsaturation then is 1/2 of 10 minus 8. No other halogens or oxygens, or halogens or nitrogens, I should say. So nothing else in our degree of unsaturation. So this is simply 1. 10 minus 8 is 2, divided by 2 is 1. And then in our IR, we see a carbonyl, C double bond O around 1700, 1750 in this case. And we see a CO here, signal around 1200, and then our sp3CHs. Okay. Not much more information we can get from the IR, so we'll move along to the C-13 NMR. So with that, we have the depth spectrum here. So again, the down signal here is a CH2, and then these can either be a CH or a CH3. And what we can tell right away is that this is what, about 50-ish, 52. This is much more deshielded than our one here at like 10. So that will tell us some information about the chemical nature of that particular carbon. And then lastly, we see the carbonyl, again, less than 200, around 180, 175. So that is consistent as well with not a ketone. So this could be an ester. We will have to see from the proton NMR if that's consistent. Okay. So now we're at the proton NMR. Again, I'm giving the hydrogen integrations instead of doing the math and measuring with the ruler here. But again, it's the same formula, same type of thing that we did in the first question. So here, let's look at our signals. So we have a CH3, a 3-hydrogen triplet at 1. We know it's a triplet because they expand it for us here. This one is very hard to interpret as drawn originally. So when expanded, this is the 3-hydrogen signal, and it's a triplet. So that's a CH3 bound to a CH2, probably. It's split by 2 neighbors at least. That's definitely true. And we know right away it's a triplet, or excuse me, we know right away this is an ethyl pattern because this CH2 is also split into a quartet, which is consistent with a 2-hydrogen signal here that's split by 3 hydrogens. So A is splitting B, right? So this is A down here, and this is B. These are the same signals, they're just expanded to give us the splitting information. So we know that we have this ethyl pattern. And the other information we see is that the CH2 is probably bound to the carbonyl because it's split, or not split, because it's shifted to around 2. That's consistent with a CH2 bound to a carbonyl. And also, since there's no other splitting pattern, splitting nature of the CH2, it's probably bound to the carbonyl, because if it was bound to another carbon bearing a hydrogen, that would cause for a different splitting pattern. And then lastly, we see a 3-hydrogen signal that's a singlet, so that must be a oxygen bound to a CH3, right? So if you're wondering, could you put like the CH3 and then the oxygen, because that would still be a singlet. The problem with that is simply that the carbon would have an expanded octet, right? If this was a CH3 bound to 2 things, that would have 5 bonds. That's impossible for carbon. So that's why that doesn't fit here. So this gives us that structure, and then let's label everything to make it consistent. All right, so here this is A and B, and this is C. So A and B and C. And then going back to our carbon C-13 NMR. Here, this is A, this is this smallest signal here, this is B. And then like I was mentioning when I was first interpreting this, the difference between A and C is significant. And that makes sense here because we just have a carbon bound to an alkyl group versus a methyl bound to an oxygen. That's a significant difference there in the shielding, in the chemical shift. And then lastly, we have our carbonyl. All right, here we have our last question of the video. So again, you should start with the degrees of unsaturation from the molecular formula. So here we have C2H4Br2. So our degree of unsaturation then is 1/2 the hydrogens for saturation, which is 2 times 2 is 4, plus 2 is 6, minus how many hydrogens are actually present, which is 4, minus halogens. There are 2 bromines in this case. So those are halogens. And then there's no nitrogen. So this is 6 minus 6 is 0, divided by 2 is still 0. So no degree of unsaturation. And here we don't see any real information from the C-13 NMR. This might be a carbon-bromine stretching here, but no real information from the IR, which makes sense because we don't have any pi bonds or rings or anything that would appear in the IR. So that is that one. That is the IR, I should say, and the degree of unsaturation. So then we move to the C-13 NMR, and we're back to our proton coupled and decoupled here. So what we see here is that these are CH2s. And we know that there's 2 carbons, and we only see 1 signal. Again, we ignore the solvent. So what this tells us is that this is symmetric. Because if it wasn't symmetric, there would have to be 2 signals. But since there's this symmetry, 1 signal can be representative of 2 different carbons that are identical, and that they're identical by symmetry. So we know all that information from just looking at the fact that there's only 1 signal. And then when we move down to the proton NMR, we see a 4 hydrogen singlet at about 3.5, and to 3.75 or so. Again, this is suggestive that it's symmetric because identical hydrogens do not split each other. So that's why these 2 CH2 groups are symmetric and identical. They do not split each other, and that's why we don't see any splitting pattern. So, and again, the chemical shift is almost at 4. So what that means is this is probably a CH2 bound to a bromine. That would push the chemical shift that far. And then we need to have a symmetric molecule. So this has to have another CH2Br, and those are bound to each other. And then if we look at our molecular formula again, it's C2H4Br2, so that's 2 CH2s and 2 Brs. So it's consistent with what we're seeing here. So if we put this into what you should show on an exam or something, it would look like this. There's your structure, and then this is the only signal, right? These are the same thing. They appear there, and then A is the same carbon up here. That is a CH2. So this one can be very tricky because it's all about the symmetry. But when you identify the symmetry, you know then that you don't see additional peaks in the carbon NMR, and that is your first indication, your first hint that this is going to be a highly symmetric molecule. So that is all I have for this video. I hope you found it helpful and you learned something. If you did, please leave a like and subscribe to the channel for more content like this. If you have a suggestion or a topic idea or anything like that, please feel free to leave it down in the comment section below, and I'll get to it as soon as I can. So with that, I hope you all have a great day, and I'll see you in the next video.